Hi there. In this particular video we're going to be looking at, well, as we can see here, logic and truth tables. So this involves things like AND gates, OR gates and inverters or NOT gates, as you'll see shortly. So what do we mean by an AND gate? Okay, let's have a look at some switches, shall we? So we could have some input here, X, and we can have a switch here in series with another switch here, and perhaps we have an output here, Y. Okay, now if this switch is open, then our input X has no way to get across to the output Y. Similarly, if this switch here, let's label them, shall we? A and B. If B was open, it would be, regardless of A state, we would not allow X to be transferred to B. The only way we can have a signal on X here transferred to B is if A and B, in other words, both A and B are closed switches. So there's an equivalent here. We can say this is an AND gate. And we write it with logic as A dot B. Okay, and dot means and in logic parlance. Okay, so that's a series circuit, and you can think of series circuits as essentially being formed with AND gates. Okay, what about our parallel circuit? Here we are. Let's draw a parallel circuit. This time we'll have the switch there and another switch here, like so. Okay, not very symmetrically drawn, but never mind. There's our input. Here's our output. This time we're going to have switches A and B in parallel. And you can probably guess that if switch A is closed, then we're going to have a path from X all the way through to Y. And if B is closed, we're going to have a path all the way through to Y also. Okay? So in this particular case, we do have an OR gate, because if A or B is closed, then signal X is going to be transferred to point Y. Okay, so we have an OR gate, and we can give that some logic parlance as A plus B. Okay, so plus this means and this plus means OR. That's really important for you to remember. Okay, so why don't we have a little look then at an array of gates now. How about a NOT gate? A NOT gate is an inverter, which means that whichever logic level you present to the input of a NOT gate, it will give you the opposite on the output. So let's draw a quick symbol for a NOT gate. Here we have it. We can have A coming in, maybe we'd have X on the output. Oh, there should be a little cap there. Okay. And it doesn't really matter which letters we use. Choose to use A and X here. And I'm going to give you possibly the simplest truth table you will ever see. Okay, so a truth table. And we have an input A. Now input A can either be 0 or 1, only one of those two states. Our output X, because it's an inverter or a NOT gate, X will be the inverse of whatever's presented on A. So if 0 is presented on the input, the output is going to be a 1. If a 1 is presented on the input, the output is going to be a 0. Okay, so there you have a NOT gate and its truth table. Maybe I can split this screen up a little bit and let's revisit our friend the AND gate. Okay, symbol is like so. We can have X here. Sometimes you'll see an ampersand there. We've got A and B as our inputs. And now we draw a truth table. Knowing that we have 2 inputs, do you agree that we may be therefore going to have 2 to the power 2, 4 possible combinations of inputs? So let's draw the truth table for this. Okay, so we're going to have a column for A, column for B, and a column for output. We normally call that X. And I'm thinking of 4 possible input combinations, so do it this way. And here's a good way to write in all those combinations of inputs. So always start on the right hand side, B, okay, and we're going to have 0, 1, 0, 1. So just flip the bits one at a time. Then move left. Rather than flip the bits one at a time, flip them 2 at a time. So we can have 0, 0, 1, 1. Okay, so as you can see here, we've got 0, 0, 0, 1, 1, 0, 1, 1, all distinct and representing all possible combinations of A and B. Now, because this is an AND gate, and remember for the AND gate we were looking at this sort of scenario, both switches needed to be closed, and we could have any letters you want here. How about Greek letter, alpha, beta, doesn't really matter what you choose, but both need to be closed for the input to be transferred to the output. Okay, so 0, 0 is no good, that's both of them open. 0, 1, no. 1, 0, no. 1, 1, both are closed. We do have an output. Okay, so there's a truth table for an AND gate. Okay, let's have a look at something we can do with an AND gate now. We're going to invert its output. And there you'll notice the word AND with an N before it, and therefore we have a NAND gate, used very frequently in semiconductor chips. Okay, symbol for our NAND gate. Well, we have the old AND gate symbol, and we put a little circle on the end there to indicate an inverter. Okay, and we could have the output, we can call it X. We've got A and B as possible inputs. This thing is actually equivalent to, or 3 bars for equivalent to having an AND gate. And the output of that is connected to an inverter, which we looked at up here, of course. Okay, so these are equivalent. There's A and there's B. Okay, and what are we seeing then for the truth table? Well, let's move across, draw a truth table in for this. Again, we only have 2 inputs, so therefore we have only 4 combinations of input. Okay, so we're going to have A here, B here. I'm going to put in Well, X is our output. Let's first of all do the AND gate. Then I'm going to put it a bar on top of X, meaning the opposite to X. Okay, so where you see a bar, we mean a NOT gate, and here's a NOT gate over here. Okay, and this can be written in logic as a dot B with a bar over the whole thing. Right, so let's fill in the truth table inputs initially. Okay, so 0, 1, 0, 1, move left, 0, 0, 1, 1. All four states are there. It's always a good idea to put the AND outputs in first, and then you just flip those bits, and then you get the NAND functionality here. Okay, so we can see over here, that's where we had our AND truth table. So we got 0, 0, 0, 1. So we invert those and we get the one that we're desiring here, this one, which is going to be flip all these bits, and maybe if I can just highlight those. So we're going to reverse those, and let's stick them in here. Okay, reverse that, reverse that, reverse that, reverse that. And there we have our truth table for a NAND gate. Okay. Now then, let me just see if I can change that color. Right. Let me move down now for yet another gate. This time I'm going to go for an OR gate. OR gate. And let's have a look at the symbol for an OR gate. Well, it looks a bit like this. Here's an output, give it any old letter, we'll call it X in this case. Then we have again two inputs, A and B. And if you can remember, the OR gate in terms of switches was very much like this. Okay, so there was switch A, there's B, here's our output X, and we can give the input any value you want, call it alpha or something. Okay, now then, let's draw the truth table for this OR gate. A bit larger this time. Okay, so we've got A, we have B, and the output X. We're going to put the possible inputs in again. 0, 1, 0, 1, 0, 0, 1, 1. So an OR gate. So if A or B are high, then the output X will also be high. So A or B, neither there, so no. A or B, yes, B is high here, so output goes high. This row here, A is high, so that's enough. Output goes high. Here, both are high, so A or B, yeah, high. So here we have a truth table, and remember the logic was A or B. Okay, so the truth table there for the OR gate. Predictably now you may think we're going to now look at a NOR gate. So an OR gate with an inverter connected to the output. Okay, so a NOR gate looks like this in terms of its symbol. And so it's an OR gate with the little circle on the end. Okay, we can call that X. We can have A and B here. The whole thing is equivalent to an OR gate connected to an inverter, like so, and that's its representation there. Okay. Now then, how about the truth table for a NOR gate. I'm going to have A and B. Okay, there's heading rows in there. Split these up. So why not do the OR function first? Okay, so basically we're looking at this point there. Okay, A or B we're looking at there, and we would therefore have our output as the inverse of that, A or B with a bar over it. Okay, put those inputs in again, 0, 1, 0, 1, 0, 0, 1, 1. Hopefully you're getting used to this now. Put the OR functionality in. Well, anywhere where there's a 1, we get a 1 out. That's what OR means. Okay, so 0, 1, 1, 1. Just invert those, and we get the NOR functionality. Okay, so NOR functionality, flip these bits in this third column here. 1, 0, 0, 0. And there you have your NOR truth table. Okay, just a few more I'd like to go through. How about an exclusive OR gate? And this is written as XOR. An exclusive OR gate. What do we mean by exclusive? Well, first of all, let's put the symbol in. Here's a symbol for an exclusive OR gate. A and B, and we will have X on the output. So an exclusive OR gate. It's exclusive because the output will only go high when the inputs are different. Okay, so just remember it that way. Right, so here's A, here's B, 0, 1, 0, 1, 0, 0, oops, 0, 0, 1, 1. Our output, we call it nominally X. So when the inputs are different, the output will go high. Well, here the inputs are the same, so it's going to be low. The bottom here, the inputs are also the same. Output's low. The second row, the inputs are different, so we have a high. Third row, the inputs are different, we have a high. Okay. And you might be wondering, well, how do you write this in terms of logic? Well, we're going to have X equals, now then, let me just see if I can highlight these two rows for you. This is going to describe the logic function for this thing. Okay. So we're going to have, well, you can see here on this second row, we've got A is low, A is low, B is high, so A and B, or the third row. So A is high, B is low. Okay, so let me just repeat that. X is equal to not A and B, in other words, A low, B high, or the third row, A is high and B is low. And that is an exclusive OR gate truth table for you. Let's have a look at an exclusive NOR gate. So an exclusive NOR gate, basically we're going to have an inverter on the output of a NOR gate, essentially. So the symbol for that, okay, so that goes in there. It has a little circle on it, meaning there's a NOT gate there, and the rest of it is just the same as the symbol for the NOR gate. So A, B, and X in there. This is all equivalent to, of course, equivalent to A, B, it's going there, that's going there, that's going into an inverter, and here we have our output X. Okay, let's draw the truth table for that. Okay, so we're going to go across, we can have A there, B here. I may as well put the other rows in now. Okay, 0, 1, 0, 1, 0, 0, 1, 1. And I've got XOR initially. I'm aiming for exclusive NOR, of course, but why not put XOR in and then just flip the bits to make it easy to conceptualize that, what that output column is going to be. Okay, so exclusive OR, we only have a 1 where the inputs are different, otherwise we have a 0. And we're going to, if you like, exclusive OR with a bar over it, which is the same as exclusive NOR. If you like, exclusive NOR. And we just flip these bits in this third column. So we have 1, 0, 0, 1. So in that case, exclusive NOR will only go high when the inputs are the same, i.e. 2 zeros or 2 ones. Okay, good. Last one I want to talk about is called the buff gate. A buff gate. So buff is short for buffer, and we can think of a buff gate as this. Okay, so here's the output, here's the input. So A goes through the buff gate, some slight amplification and signal strengthening, but effectively X is just what A is. Okay, but it can be presented to many more gates, and a bit of an electrical issue here. It's a very, very handy gate, and you could think of this as being equivalent to A being fed into a NOT gate, and the output of that NOT gate being fed into another NOT gate. When you have NOT, you have the original. Okay, and a very simple truth table for this. It's basically, we're just going to have A here. A can be 0 or 1. Our output X can be 0 or 1. So it's not useless, it's actually very useful, because we have things like terminology such as fan in and fan out for gates, and it's all to do with how much current and voltage drops are going on within circuitry. We don't need to worry too much about that. So essentially we've looked at quite a number of gates here, a NOT gate, an AND gate, a NAND gate, an OR gate, a NOR gate, an exclusive OR gate, an exclusive NOR gate, and finally a buffer. Okay, so if you can commit all of those truth tables to memory, that would be really, really useful, and if not, just use basic logic to derive them in the future. Okay, thanks for watching, and speak to you in the next video.